Okay, so now that we know how to talk about concentrations of solutions, we can start to use concentrations as a part of our problem-solving methods. You've seen this 100 times by now. If I want to relate a measurement of A to a measurement of B, I can't do that relationship directly. I need to first convert from mole to moles of A, and then I can go from moles of A to moles of B through stoichiometry, right? But how do I get from A to B if I have a solution? I can't measure out the mass of the solution because most of it's just solvent, it's just water. If, for example, I had a problem like this, a reaction of hydrochloric acid with magnesium hydroxide, and I know that I've got a concentration of hydrochloric acid solution of 0.34 molar, concentration of magnesium hydroxide solution of 0.25 molar, and 30 milliliters of the magnesium hydroxide. Well, how many milliliters of hydrochloric acid do I need? Here the magnesium hydroxide is A. Our measurement is 30 milliliters. Instead of grams or something, we're going to use the volume. So how many milliliters of the hydrochloric acid do we need? Well, in order to go from the milliliters of A to the moles of A, we need to know that moles is equal to the concentration times the volume. Concentration in molar concentration is moles per liter. And so if I take moles per liter and I multiply it by the volume in liters, that'll give me moles. Just like if I had grams of A and I divided by the molar mass of grams per mole, that would get me the moles. Okay, and then we can get from moles of B to milliliters of B with that same formula. The volume would equal the moles divided by the concentration. So let's put it into practice with this problem here. If I start with my 30 milliliters, 30.00 milliliters of the magnesium hydroxide. And we can frame this as one big long dimensional analysis problem. Now, you could convert your milliliters into liters, and then the answer you got for the hydrochloric acid would also be liters. And you'd have to, I suppose, convert it back to milliliters. We can just skip that conversion since we would be doing it both ways. We can just deal with milliliters. So 0.25 molar means 0.25 moles of magnesium hydroxide for every 1 liter. And looking at our stoichiometry, we've got 1 magnesium hydroxide gives 2 hydrochloric acids. So we'll say 1 mole of magnesium hydroxide is 2 moles of hydrochloric acid. And then the hydrochloric acid concentration is 0.34 moles per liter. So 0.34 moles of HCl is 1 liter of HCl. And so here you see how the liters will cancel out and we'll actually be left with units of milliliters. And so we never needed to make that conversion. You know, if we wanted to, we could divide by 1,000 here and then multiply by 1,000 there, but that's just a waste of everybody's time. So what does this equal to only 2 sig figs? That's 44 milliliters. That's the volume of hydrochloric acid. So you can see how dealing with concentrations is going to be as fundamental and useful as dealing with molar masses. Whenever we have solutions, weights are pretty useless. Again, because if I weigh out this 30 milliliters of magnesium hydroxide probably weighs about 30 grams, but most of that is just water. How much magnesium hydroxide is going to be a small fraction of the total mass. Okay, so let me go ahead and erase that. talk about our next topic, which is dilution. So dilution is what we call it when you add more solvent to a solution to reduce its concentration. And when you add solvent, the number of moles of solute don't change. So if I have the concentration under the initial conditions times the volume under the initial conditions, that's going to equal moles of solvent. Of solute. I'll just change that V into a U. Okay, that is the moles of solute, the molar concentration times its volume. Well, after I have added some solvent, then the concentration will have changed. So we'll have C2, and the volume will have changed as well, V2. But because I didn't add or remove any solute, that should equal the moles of solute as well. That's constant. And anyway, of course, this implies that C1 V1 is equal to C2 V2, and that is the dilution equation. And so we can answer a question like, let's say, how many milliliters of 0.500 molar NaOH are used to make 250.0 milliliters of 0.100 molar NaCl. Okay, this is a typical dilution type problem. We've got some concentrated stock solution, and we want to make a more dilute solution, and we want to make a particular volume of that. And so we'll just put our numbers into the dilution equation. C1 would be 0.500 molar. V1 is the unknown. C2 is 0.100 molar. And V2 will be our target volume. So this is our target concentration and our target volume of 250 milliliters. I actually didn't solve this ahead of time, so give me half a sec. Here, I'll let you see me do it. What do we have? 0.1 times 250, times 250 divided by 0.5. That's going to be 50 milliliters. So V1 is equal to 50.0 milliliters. That is the dilution equation. Now sometimes sorry, give me a moment. Sometimes we'll simplify a dilution problem by just talking about the dilution factor. And the dilution factor is V1 over V2. So what this means is that C2 is going to equal C1 times the dilution factor, which is just a rearrangement of the dilution equation. But we could answer a question of like, what dilution factor is needed to reduce a 0.500 molar solution down to a 0.100 molar solution. So what would be the dilution factor in this case? Well, it would be 1/5. So V1 over V2 is equal to 1/5. And that means that whatever volume you want, you're going to have to use 1/5 of that volume in the stock concentration. In our earlier problem, we used 50 milliliters of the stock in order to make 250 milliliters of our target dilute concentration. So that is the dilution factor. It just is maybe a little bit more concise way to talk about dilutions. Okay, so next we want to talk about electrolytes. So an electrolyte is a substance which, when dissolved, produces ions in solution. So we're going to talk about three different types of electrolytes. So there's non-electrolytes, which I guess are not electrolytes. So we're going to talk about two types of electrolytes and then about non-electrolytes. So non-electrolytes, weak electrolytes, and finally strong electrolytes. And I guess before we get into this, I should explain why they're called electrolytes. Water itself is actually a really poor conductor of electricity. It has a resistance of, I believe it's about 18 mega ohms per centimeter of distance, which makes it a very good insulator. But you're probably aware that water in the real world will conduct electricity. That's why we don't want to be using anything that's plugged into the wall while we shower or bathe or swim. And that's because if any electrolytes are dissolved in water, then the conductivity of that solution rises dramatically. And so unless you're showering with distilled water that has no ions in it at all, then your shower water or pool water or bath water is actually probably a pretty decent conductor of electricity, and that's what makes it a danger for electronic devices. So that's why we call it electrolytes. The other context where you'll encounter electrolytes that has nothing to do with electricity per se, and that's like sports drinks or isotonic solutions that you might be given in a hospital or a doctor's office. So electrolytes in that case are the very same thing. They're solutions of water that contain ions, but of course they're important to us for biological reasons. We need to replenish those ions as we lose them through sweat or whatever else. And so, a sports drink is an electrolyte because it contains ions. Also, I suppose a sports drink would be a great conductor of electricity. All right, so what are non-electrolytes? These would be molecular compounds. Which dissolve in water, but do not break apart. So, for example, oxygen is a molecular compound, and oxygen will dissolve in water, and it will produce oxygen aqueous. Well, there's no ions to be seen, and so oxygen is a non-electrolyte. Another non-electrolyte would be sugar. So when sugar is dissolved in water, it doesn't break apart to form ions. It is a non-electrolyte. And this will make a lot more sense as we sort of contrast non-electrolytes with weak electrolytes. Okay, so weak electrolytes produce a small number of ions. So weak electrolytes are weak acids and bases. Weak acids and bases will produce ions. For example, let's look at NH3. NH3 plus H2O liquid is going to produce NH4 plus and OH minus. We're very close to the edge there. It's all in. We're good. Okay, so it is going to produce ions, but ammonia is a weak base. We have an equilibrium arrow here, and you may recall that it's maybe only about 5% over here and 95% over there. the weak acids and weak bases will really be strongly reactant favored, and so there's not very many ions produced. So a solution of ammonia, it will conduct electricity, but it won't do that very well. It will offer substantial resistance to electricity flowing. Weak acids and weak bases are the weak electrolytes. So what are strong electrolytes? Well, how about strong acids and bases? So let's take HCl, for example. HCl is going to form H plus and Cl minus, and it's going to do that 100%. So lots of ions with an HCl solution. Also, soluble salts. And so something like sodium chloride, if I put solid sodium chloride in solution, it's going to produce Na plus and Cl minus. Again, it'll do that 100%. And so it is a soluble salt and a strong electrolyte. That's all you really need to know about classifying electrolytes. Soluble salts are strong electrolytes. Strong acids and bases are strong electrolytes. Weak acids and bases are weak electrolytes. And then molecular compounds are non-electrolytes because they will dissolve but not form any ions. And you could say other things like, say, most metals or insoluble salts. I suppose they're non-electrolytes as well, if only because they don't dissolve at all. Okay, so in biochemistry, ions play a critical role in our blood, in our cytoplasm within the cell, other bodily fluids. I suppose just about everywhere we've got ions performing critical roles. There's a little bit of a different language that we'll usually use when we're talking about electrolytes in biology. And so we'll introduce a new term, an equivalent. So an equivalent is the number of ions which carry 1 mole of charge. 1 mole of charge. So in other words, 1 mole of Na plus is equal to 1 equivalent. 1 mole of calcium 2 plus, however, is going to be equal to 2 equivalents, because each calcium ion carries a charge of 2 plus. We could say 1/3 of a mole of aluminum 3 plus, that's going to be 1 equivalent. Each aluminum carries 3 charges, 3 fundamental charges, and so you only need 1/3 of a mole of aluminum to equal 1 equivalent. So hopefully that is straightforward enough. But we also want to recognize that some salts are more massive than others. So sodium chloride versus potassium iodide. Potassium is heavier than sodium, iodine is heavier than chlorine, and so if I wanted to create a solution that had the same sort of electrolytic strength, if it has the same concentration of ions, then I'm going to need to weigh out more of the potassium iodide in grams than I will of the sodium chloride. And so a gram equivalent is just the number of grams that are required to produce one equivalent's worth of charge. So a gram equivalent would be the molar mass of an ion divided by the charge of that ion. So the molar mass divided by the charge of the ion would give you the gram equivalence for that ion. And so how many gram equivalents are in NaCl, for example? What are the gram equivalents for sodium chloride? Well, our molar mass for sodium chloride is 58.44 grams per mole. And then sodium chloride is going to have a 1 plus charge on the sodium and a 1 minus charge on the chlorine. So we'll add those two together. There's a total magnitude of the charges in that compound of 2. And again, I didn't work this one out ahead of time. Sorry, I seem to have overlooked a couple of these problems. So 58.44 divided by 2. It's going to be 29.22. So 29.22 grams per equivalent. In other words, if I weigh out 29.22 grams of sodium chloride, then that will have 1 mole of total charge, a half a mole of positive charge and a half a mole of negative charge. And I could use that to sort of make a solution that has the desired amount of charge. More realistically, things like our bodily fluids, for example, are going to be in milli-equivalents per liter. And sorry, I do have that figure up. I just need to navigate to it really quickly. Oops, is that it? Nope, almost. Okay. Oops. No. There we go. All right, so sorry. There we go. So this is actually not a textbook figure with a number, but it's from the chemistry in action section in our textbook, and it's showing you the concentration of different major electrolytes in blood plasma. So sodium and chlorine are the majority components of electrolytes in blood plasma, and you'll notice it's on the order of 100 milliequivalents per liter. Other ions are far smaller, 2 to 5 milliequivalents per liter. So if you wanted to create an isotonic solution that had similar concentrations, then for example with milliequivalents per liter of about 100 milliequivalents per liter, and with the gram equivalents of sodium chloride of 29.22 gram equivalents, let me get rid of the figure viewer, there we are, then I guess you'd want about 2.9 grams of sodium chloride in 1 liter of isotonic solution. Don't quote me on that, or you may put your patients at risk, but that would be an approximate amount of salt that should be in an isotonic solution. Okay, we'll pause this video and start another one for the next section.